Swayam Prabha. Digital India. Educated India.
Okay, so our original discussion was, yes, we have an electrical field, we have a magnetic field, and electrical field is actually stronger. So that is the thing, it is going to affect strongly with my system. Now, how this interaction happens? So I have an electrical field from my electromagnetic radiation, which I am defining as E. So what I'm trying to do right now, trying to get a parameter or a mathematical equation so that I can quantify things. So an electrical field I have, and this electrical field is going to change the electronic distribution in a molecule. So can anyone name a parameter which connects to a change of the electronic distribution in a molecule? Any parameter that defines electronic distribution or electron distribution?
Sir, dipole moment could be the option, electron parameter.
Okay, good. So dipole moment not exactly is connected to the electronic distribution. It actually is a direct effect of its electronic distribution. So the direct parameter that connects is known as the polarizability that you have learned, right, during the Raman spectroscopy especially. So polarizability given by this Greek term of alpha, and then if you combine them together, what is the effect of this electric field on this polarizability, then you go to this factor known as dipole moment. So dipole moment is more of an effect that it is created when we are putting an electrical field around a system. So that means we are going to create a dipole moment in a molecule when it is interacting with this electrical field of an electromagnetic radiation. And that is going to create the electronic transition. Okay, so over here I'm going to take a few seconds. So electronic transition is going to happen. What is it? Electronic transition means it is the electronic redistribution. What it is redistribution to? From a ground state electronic wave function to an excited state wave function. Why it is happening? Because the electric field of an electromagnetic radiation is affecting it. The effect can be parameterized with the polarizability, and that is factored by this dipole moment. And this dipole moment, because it is creating this electronic transition, is known as the transition dipole moment. And now, with the very minimal mathematical knowledge I have, if I want to write it down, the probability of the electron transition for this particular system can be written as psi excited state. We are going under this influence of this transition dipole moment over here from the ground state, and that I have to take from minus infinity to plus infinity. That means all the space possible, while this is I am actually doing this integral over a small volume. And this equation most of you have seen earlier, and that is what is the physical origin of that. This transition dipole moment is coming because of the light matter interaction and how the light electrical field is interacting with the electronic distribution of a matter or electron. And this value of this integral can have two values. It can be 0, it can be 1. If it is 0, then it is called a forbidden transition. The transition is not possible. If it is 1, you can say it is a allowed transition. So how do we know it is an allowed transition or forbidden transition? There are two ways you can do that. One is looking into the molecule, find out its symmetry, and each of this ground state or excited state, you can put it with a symmetry representation, which can be found in the character table. And from there, you can put all those things over here. And this dipole moment is generally represented by the X, Y, or Z axis on that particular character table. And then you can do this calculation from the character table and find it out whether it is a 0 or 1. I'm not going into the details. It will be covered by Professor Leela in the second part. The second one we can do just by using our chemical knowledge, that whether it should be allowed or not. And in most of the time, to be honest, what chemists do, they do the experiment first and find out whether it is giving you a strong absorbance or not. And from there, we back calculate, try to find out what will be the actual molecular distribution during this electronic transition. So let's look into this equation that we already know for that. But before going further, just to double check, we understand it properly. An electrical field of the electromagnetic radiation interacts because it's stronger compared to magnetic field. It interacts with the electronic distribution given by the polarizability. If we combine them together, I get a dipole moment. This dipole moment is created during the interaction between the electromagnetic radiation and the matter. So it is a very transition dipole moment. That means it happens only during the transition. And this is the equation we use, which is known as the probability of the electronic transition, or sometimes integral dipole moment system, which is actually giving you an idea whether this transition will be allowed or not. Now this equation we already know from our knowledge, which is given by absorbance of a molecule is equal to epsilon Cl. And this equation is known as the Lamberts Law. So let's connect it. What is those things? So generally what we do, we generally take a sample in a cuvette. We pass a light. We find out its intensity. Say it is I0. If this molecule is absorbing, on the other side, I'm going to get a different intensity of light, say I. I take the log of I0 versus I, and this is defined as the absorbance, or A. Now, what are those epsilon C and L, all those things coming into? So over here, the intensity of the light changes. Why? Because the molecule is changing its electronic distribution, and that needs energy. And that energy is taken from this incoming light, and that is shown during the outgoing light. The sum of the portion of the energy is missing. Why? Because that energy is used for this electronic redistribution, or what we say as electronic transition. So that is the electronic transition we are talking about. So it goes to the excited state. And this energy is sapped from here. Now, what are the factors it is going to contribute over there? First, say I have two samples, same sample, but different concentration. This is much more concentrated. This is less concentrated. So who will be absorbing more? So obviously this is going to absorb more because you have more molecules present there. So more molecules means it has more chance to change its electronic distribution, and more energy will be absorbed. So that is why concentration is a factor C, which is directly proportional to the absorbance. Now say I take the same sample, same concentration. But the shape of the cuvette is different. one is longer than the other. Who is going to absorb more? Because the light has to pass through this. So this is the region it has to cover. Similarly, this is covering this area. So you can see this is covering much more larger area compared to here. So it also depends how much of the sample is exposed to light. And that is given by this particular term called path length. That means how much length in that particular cuvette which contains my system or solution is allowed to interact with the incoming light. So this is given by this term L. So obviously absorbance is directly proportional to L. Now comes the third term, the epsilon value. So what is this epsilon value? Now say I actually take two cuvettes, same size, path length same. Same concentration, but what is different is my sample. This is a sample B, this is a sample A. Same concentration, same path length. Are these two systems going to show the same absorbance? Not really. The absorbance can be different. And in most of the time, they are different. Why? Because there's one other system is also very important. What is the identity of this particular molecule? Because depending on the identity of the molecule, whether it is A or B, it is going to interact with this electromagnetic radiation differently. So there should be a particular factor which is going to relate how the interaction is happening between the molecule and the electromagnetic radiation. And that will be something of a molecular property. And that is given by this epsilon system, which is known as molecular extinction coefficient. And this is actually a very unique property for each of the molecules. So until there, I think most of you already know. But now I want to understand what this molar extinction coefficient actually is. What is the physical understanding for that? So let's go back to the molecule one more time. So say you have two molecules. This is the electronic distribution for molecule A. And here comes my incoming electrical field. What is going to happen? This is going to change my electronic redistribution, right? And during that, what is the actually happening between the electrical field and electronic environment? So over there you have to understand this electronic distribution that molecule A has. It is nothing but a wave function, right? It is a ground state. So I can say it is actually having a wave function. And over there, you are bringing a different wave, that is electromagnetic wave. And altogether, what I'm going to see is a different kind of wave. The wave nature is changing. Just very simple understanding, you can say there is a small wave before, you bring another small wave, combine them together, you get a bigger wave. Because the wave function is defining how the electron is distributed, you can say it is going to a totally different wave function. And that is what is happening. So that means we can define the interaction between the electromagnetic radiation and an electrical field of a molecule through the interaction of waves. And how the wave interaction can be defined? It's defined by this very important term, oscillation. How much oscillation can be transformed between them? And there is going to be a term called oscillatory function, which is going to define how good the interaction between this electromagnetic radiation incoming and this existing electronic field is going to happen. And that will all depend mostly on this wave function, because this electromagnetic radiation incoming is going to be constant for most of the molecules. What is going to different molecule to molecule is this electronic distribution over here, and how much it can interact with the incoming interaction and how much it can oscillate, the oscillatory function. So what is the oscillatory function in mathematical? So this oscillatory function defined this time by FEQ is given by this particular term. Don't need to remember it. I'm just giving you the number for your sake of understanding. A particular constant into nu1 to nu2. This is the frequencies between which I am measuring a particular absorbance band, d nu. This epsilon nu is the function between which a molecule can interact. For an example, say this is the absorbance, this is the wave frequency. So I'm measuring a frequency between nu1 to nu2, and what I see, there is a band like this. And over there, what I'm going to do is take the area under that. So how that area will look like this, or like this, or like this. It totally depends how the molecule is interacting with the electromagnetic radiation, how the molecular electronic distribution is behaving, how much it can exchange the oscillation. Depending on that, this area will change, and this area is defined by this oscillatory function. And over there, the interchange is actually defined by this molecular extinction coefficient value, which is defined by this particular frequency. So that is why for each of the band, when you actually report for a molecule, we always try to say what is the epsilon value, molar extinction coefficient value, and the next question we ask, at what wavelength, because it is totally wavelength dependent. Because the wavelength dependent means it knows that exactly which particular region of the electromagnetic radiation I have to interact, and that counterintuitively saying to you that which particular region of the wave function of the existing electronic distribution is going to interact. Okay. Now, this oscillatory function is the main reason why it is a molecular property, because it defines how the actually in molecular level the light and matter actually interacts. Okay, so this epsilon value will be very much a property of that particular molecule. So the concentration, the path length that we found from this equation by Lamberts law, these can be controlled from outside, but this epsilon value is a constant. Molar extinction coefficient is a constant. You cannot change it. For a particular molecule is a constant. So that is a good thing, because with respect to that, you can find out molecular properties. And that we have done earlier. So over here, I'm going to show you different kind of electronic transitions. And I'm going to tell you how the epsilon value is going to differ. So again, this epsilon value is coming from this equation of absorbance equal to epsilon into C into L. What will be the unit of absorbance? Absorbance doesn't have any unit because it is a ratio of intensity of light, log value of the same thing. So it will cancel each other out. So absorbance value doesn't have any unit. C is going to have a unit of concentration, molar in general, that means moles per liter. L is going to have a path length unit of a distance. So generally it's given in the centimeter. Why? Because practically we use a cuvette of 1 centimeter path length size. So with respect to those things, what would be the unit of epsilon? This is unitless. This is having a unit of molar, this is centimeter. So obviously this is going to be mole inverse, centimeter inverse. Now, different transition we are talking about. Pi to pi star transition we are talking about. They have a strong epsilon value greater than 10,000 mole inverse, centimeter inverse. That means it is a very strong allowed transition. Now coming back to that visualization, what Harjit was trying earlier, what we are talking about, say we are talking about a carbon double bond oxygen system. So it has this particular pi bond. From there, it is interacting with an incoming light and redistributing this electronic electrons to its pi star orbital. So that is what we mean by pi to pi star transition. This electron redistributes such a way that some of them come here, some of them go here, they change in symmetry and all those things, and you end up with this particular final stage. And that is what is known by electronic transition. It is very much allowed because of the symmetry parameters. Again, it will be taught by Professor Leela later. The symmetry allowed transitions. So that is why it is actually can have a huge oscillation exchange between the incoming light and this orbital. So this interaction between this incoming electrical field and the existing magnetic field depends on different factors. One of the factors is symmetrically allowed or not. That means, is there symmetry matching or not? If the symmetry matches, that can have a very strong interaction, very strong exchange of oscillation, shown by very high value of epsilon. If you go to the similar kind of molecule, but N to pi star transition, N means a lone pair on the oxygen. It is exchanging to the pi star. There you see the value a little bit lower down, 5,000 to 10,000 unit or so, which shows that it is still allowed, but not as allowed as pi to pi star transition. Why? Because the overall distribution of the electron is such that when you are trying to redistribute itself, it is not that easy to do, symmetry wise, energy wise, all those things, and that is reflected by a little bit lower value of epsilon. Then comes DD transition, especially the transition metals. They generally have a value between 100 to 1000. That means they are allowed with respect to the spin, but with respect to the orbital, they are not allowed. They are orbital forbidden. The symmetry of the orbital doesn't allow it. So that is why the oscillation exchange doesn't happen that easily, reflected with the epsilon value. Why this huge range? That is because it depends that can you break the symmetry a little. If you put some p orbital contribution to the d, that has a little bit more probability, and that increases the epsilon value. If you don't have that much interaction, it will have a lower value of epsilon value. So by looking into these values, you can have an idea how much interaction between a p orbital and the metal d orbital is happening. And the p orbital interaction typically comes from the ligand, so you can have a very good idea how the ligand and metal are actually interacting through. The other one can come DD transition, but for an example, a Mn+2 high spin system. That means a D5 system. A D5 high spin system, you have a value between 0.1 to 1, or sometimes even go to 10. This is because it is spin forbidden. Orbital forbidden, it was already there. So it is very little chance of an exchange of this orbital, the oscillatory motions between them. And that is reflected over there in the values of this manganese. So that is why you can see a manganese +2 solution in water, very light pink, whereas other fast flow transition element give much more deep color. So that is what it is actually happening there. So that is what is happening during an absorbance. So the main take-home messages over there for this particular class is the following. Electronic transition, when it happens between a light matter interaction it happens mostly due to electrical field is actually interacting with the electronic field created by the electron itself. So it is a electron distribution that is getting affected. The transition is actually depends on the polarizability and the electrical field. So polarizability is a property of a matter, electrical field property of this light or the incoming electromagnetic radiation, and that is given by this transition dipole moment. And this transition dipole moment can be used to find out what is the probability of a particular transition. If I'm going to an excited state, operator will be this particular transition moment from the ground state, the d tau. If it is 0 or 1, depending on that, I can say it is disallowed or it is allowed. And the other important thing we'll learn, absorbance equal to epsilon CL, that we already know, but what this epsilon value is coming from. We found it is connected to this particular factor known as oscillatory function, because that is an interaction between the electrical field waveform and the electronic distribution waveform of the molecule. Okay, so we'll stop over here. We'll ask for any question any of you have, and the next class we'll go for this transition between the molecules for an optical active molecule. Yes,
hello, sir.
Yes.
Sir, LMCT and MLCT lies in which range in terms of epsilon?
So LMCT and MLCT generally lies somewhere in between there, and it depends on like how much of the LMCT and LMCT you are doing. For an example, it depends on that symmetry and other factors, how much it is allowed. For an example, you have already seen that MLCT transition, if I want to see, you will find that the 4D or 5D orbital containing molecules can exchange the electronic transition better compared to a 3D. Why? Because 3D orbital electrons are much more strongly contracted, much more closer to the system, and that is why a change in those distribution will be a little bit trickier. Whereas 4D and 5D are much more diffuse, a little bit less control from the nuclei. So that will be much more easier to change those things, and that is easily reflected on their epsilon values. So that is why MLCT and LMCT have a range, and it also depends on which particular ligands, which particular metal you are using. If you are using much more diffused orbital system, you are going to have little bit larger MLCT or LMCT values. That is for the physical understanding. If you want to go a little bit more details, you have to look into the symmetry of that.
Okay, sir. Okay, sir.
Okay, thank you. Any more question?
Hello, sir.
Yes, sir.
Sir, you have told that that the optical activity is due to the electric field only mainly triggers the optical activity. Means when we have put any optically active compound, so the electric field and magnetic field both actually interact with the molecule. And
so I will stop you over there. I didn't say that optically active molecule only interact with the electrical. I told you the optical absorbance is mostly triggered by the electrical field. I haven't come into the optical activity yet.
Okay, sir. So so absorption, so yes. Whatever, sir, that means both interact with the electric field and the magnetic field both.
But the electric field is going to affect more. But why optical activity is happening, that is a different scenario that we will discuss.
Okay, sir. Yes, I understand. Okay, sir.